breakable. All right, I think we are ready to go here in just a minute. Trying to get everything set up with the settings. Welcome to episode 7 of hardware hacking. In this session, we'll dive directly into the SCA101 Lab 3.2. Recovering data from a single bit. All right, welcome back. Today we're going through the Chipwhisperer's recovering data from a single bit lab. The goal is to show that even if a device only leaks 1 bit of information per operation, we can still recover a secret AES key byte. So far in this series, we've seen that power consumption depends on the data being processed, then modeled with things like Hamming weight. In this lab, we'll push that idea to an extreme. We compress each trace down to a single bit, and we'll still pull out the key using statistics. This notebook uses a simplified AES-like function. We're not implementing full AES here. Instead, we focus on 1 byte. We XOR it with a key byte and pass it through the AES. That's enough to capture the core leakage behavior that real power analysis attacks exploit. We'll pretend that some internal node of that function leaks exactly 1 bit. Our attacker knows the algorithm and sees all the inputs in that 1 bit of leakage, but doesn't know the key. The attack scenario we're simulating here. The learning outcomes for this lab will be to understand some basics of the AES algorithm, see how a single byte of leakage can translate to a full key reveal, and to see how to sort and ranking lists. At the end of this lab, we'll be an expert AES, which stands for Advanced Encryption System. Remember that the input data flow for AES, something like this. We have an XOR gate. We have a key that's passed, and that's what that AES key. We have input data. Put this in dark mode so we can't really see the text. That change the theme. You can see AES key XORed with the input data, and then pass through an S block. I do like the dark mode, but hard to see sometimes. First, let's build our AES model. I'm going to make your life slightly easier by giving you the S block. Before proceeding, I just want to confirm that the audio is coming through decently on the stream. It seems to be fine. So here we have an S box and a 16 by 16 matrix. This is a nonlinear substitution step in AES. It takes an 8-bit input and swaps it for another 8-bit value. We're going to treat this as a black box. The important part isn't how we build it. It's the small changes in the input that they produce complicated changes in the output, which is perfect for side channel analysis attacks. Here is the Wikipedia definition of what an XS is. Rindale stands for substitution box, known as a lookup table, which is an array, replaces runtime computation of a mathematical function with a simpler array indexing operation. In cryptography, an S-box is a basic component of symmetric key algorithms, which AES is a symmetric key encryption algorithm. They're typically used to obscure the relationships between the key and the ciphertext. And the inverse of the S-box is used to decipher, where the forward S-box is used to encrypt. The S-box by Rindale is typically designed to be resistant to linear and differential cryptanalysis. This was done by minimizing the correlation between linear transformations of output and input bits, and at the same time minimizing the different propagation probability. We're going to go ahead and run this cell block. I do want to restart the kernel, and then also reset the device. Unplugging it, waiting a few seconds. Then plugging it back in. Okay, so at this point, we're going to run this cell block again to initialize the S-box, which should be enough for us to build a simple function that XORs a secret key value with the input data and then performs a lookup in the above table. Before we continue, modify the following code block to implement the correct function. The function is called AES internal. We have a definition statement here where we pass in the input data and the key into this function. So for the return, we're going to return the S-box, which is the input data XORed with the key. So let's run that statement. Now we're going to run the test vectors. If the values are not as expected, check your implementation. If the following executes without error, we'll go into the next part. These asserts are just test vectors. If the implementation is correct, we get the expected output. and the cell prints that it's okay to continue. Will be our sanity check that the core function we're attacking behaves like we expect. So we get the okay to continue. So now we'll make a new function which does not expose the key. The following function has some hard-coded key. You can change this key byte if you'd like and see it recovered at a later step. Now, in this part, we hide the key inside a route function. AES secret hard codes a secret key 0xEF. And it calls our internal AES-like step. In a real device, this would be stored in hardware or firmware somewhere you couldn't read it directly. For the rest of the lab, we'll pretend we don't know this value of EF. Our job is to recover it using only the inputs of 1-bit leakage. At this point, we can get the value of some internal part of the AES algorithm. For our first attack, we're going to assume that we can't observe this entire value. Let's just observe a single bit of the value. Imagine that someone put a probe down inside the chip to get this. We can do this by simply throwing away all the other data besides a single bit and only expose that single bit to the observer. Let's build the watcher now. Something that's optional. If we want to experiment, we can change this key byte and rerun the notebook. The attack should still recover whatever key we put there as long as the rest of the code is correct. The watcher is going to observe a single bit of data. We'll need to build lists of input we feed to the algorithm. We're just going to send in 1,000 random bytes that get encrypted, as well as lists to hold our observation. In case you're still picking up Python, here are a few handy things you might need in this section. These are some useful functions and some hints. We can use this function to generate the random data, importing the random library, calling on the randint function, numbers between 0 and 255. Here's a function. List comprehension can be used to shovel data through a function. We return a input data is equal to an array of items. Data is equal to number plus 4. Great. The input data array is. And use this while ignoring the index variable too. Fair enough. Your first objective is to build a list of data you are encrypted. Your first objective is to build a list of data with AES secret. This should be a 1,000 item random number, which ranges from 0 to 255. Call it input data. For example, if you print the input data list, it could look something like this, where there are 1,000 elements in total. Fill in the code, make a list of 1,000 random values in the correct range. Before we attack, the notebook reminds us of a couple Python tricks to generate random bytes and list comprehensions to run a function over a whole list. We'll use both and build our data set. For the input data, we're going to set that equal this. Something similar to that anyway. We're going to call in random, rand int, between 0 and 255. For items in the range 0 through 1,000. So here we're going to generate 1,000 random input bytes. Each one will be fed into our secret function. That gives us 1,000 traces to work with, which is our sample size for the attack. So now we're going to check that we really have 1,000 inputs. So these are some simple test vectors if you get the check mark printed all okay. Now we're going to feed all those inputs through the AES secret function because this is a secret function. We are only going to observe a single bit of output, which is known as the leakage. The following will perform the encryptions and mask all of the lowest bit for you, and build a new array called leak data, which contains just the 0 or the 1 status of the lowest bit. So this is going to simulate our side channel. For each input byte, we call AES secret, then AND the result with 0, 1. The mask keeps only the least significant bit and discards other 7. So leak data is just a list of 1,000 values, each either 0 or 1. We can think of this as a very simple probe attached to 1 bit of an internal bus inside the AES implementation. As you can see here, a list of 1,000 values, which are either a 0 or a 1. You can also plot, for example, the patterns of 1s and 0s. This gets pretty So let's just look at a few hundred transitions. Printing it, we can see it's just a long series of 0s and 1s. The plot for the first 200 samples looks like random digital noise, but it's really not random. These bits are determined random inputs plus the secret key, which is EF. And from the attacker's point of view, this is all we get. 1,000 input bytes and 1,000 leaked bits. The challenge is to reverse engineer the key from this. Do you think we'll be able to get something useful out of this? Let's attack and find out. AES guesser. The attack is pretty simple. Let's just use our model of the device. We know that the encryption does, after all, we know what the encryption does after all, not just a secret key. And we'll feed in the observed data for each possible value of the key. And then we can observe how many of the keys result in the observation and simulation matching each other. If observation and simulation match, this suggests our simulation is running in the same setup as the implementation we are attacking. First, we're going to build a function to count the number of elements in a list that match between two lists. That means the same value of the element at the same list index. An easy way to just iterate through the number of elements in the list. An easy way is to just iterate through the number of elements in the list and count the number that are the same. We're going to fill in the following code block. There's already some bound checking. Let's get started. We have a helper function called numSame. If the length is not equal to the length, we print arrays must be the same length error. If the maximum is not equal to the maximum of the other list, then the array maximum should be the same. So here we're going to count how many list items match up. Let's set a variable to keep track of that. Then we're going to traverse with our loop counter I in enumerate. If A equal to B, and increment our same value by 1, and then we return same. So this is going to count how many entries match between two lists. We also are going to include some basic sanity checks. The lists must have the same length and they should share the same maximum value. For our leakage, that's just going to be 1. We'll use this method as a simple scoring function. The more positions where our predicted bits match real leaked bits, the better that the key is guessed. We're going to run this. The asserts here confirm that identical lists give a full score and partially matching lists give lower scores, which is exactly what we're going to need for the attack. We get the okay to continue. The next block is the most important. You'll need to apply a leakage function. Is for each known input byte. Through AES internal function, the value of key guess is just integers 0 through, which are when all the bits are 1. Every possible value of the key byte. We'll compare the number of matching bits between our observed data bit and the hypothetical. We have our leaked data bit, and then we have our hypothetical. We have our observed, and we have the hypothetical. So we have a guessing loop here. For some guess in the range of 0 to 256, we're going to get a hypothetical leakage list. So we're going to call the AES internal function here. We're going to set the parameter of our key to a guess. And then we're going to input a byte. We're going to perform an AND operation with 0, 1. Or input byte and input data. We're going to use our helper function same count. And then we're going to print the debug. So this is really the heart of the attack. We loop over all 256 possible key bytes from 00 to each guess. We build hypothetical leakage. Every input byte, we run our AES-like function with the guessed key, then mask off the least significant bit, which gives us a predicted leakage bit for every trace under that key hypothesis. We then compare that predicted 1000 bit pattern to the real leak data and count how many positions match. Same count is our score for the key guess. If our key guess is wrong, about half the guesses should be wrong. Looking through the list, you'll see that most of the bits same numbers will be around 500, but scroll down to the correct key value, which should be EF, because we haven't changed it yet. And with any luck, that number should be fully correct, 1000 matching bits. This is only possible if the internal secret key byte matches. All right, so we have a lot of guesses here. If you look at the printed scores, most guesses are around half the bits matching, since they're essentially random. But one specific key here, 0xEF, stands out with a much higher match count, which should be about 1000. Let's look for that. Right here. Is our signal. The correct key guess produces predicted bits that line up almost perfectly with the real leakage, because we're modeling the exact internal operation that's leaking. Even though we only have one bit per trace repeated 1000 times, the statistics are strong enough to single out the right key. Now, a handy thing to do will be to sort based on the values by number of bits, so we don't have to look through that list. An easy way to do this is with NumPy arcsort. This returns the indices that would sort the list. Are small. Take the following, for example. So here we're printing the array 03412. You can cast the above to list type if you want to get rid of the array type around. Notice that this is the position of each from lowest to highest. We can reverse this to give us a highest to lowest sort instead. The NP arcsort doesn't sort the values directly, it returns the indices that would sort the list. As we can see, this is 2, index 2, index 1, then 5, 3, and then index 0. Taking our previous code, simply make a new list which contains the number of elements which are the same, where the list index is the key guess, rough outline, see the following. We'll need to add hypothetical code back in. We're going to import numpy as np. We're going to initialize a guest list. We're going to create a loop. We're going to call the hypothetical leakage, and we're going to set that equal to our AES internal function. We're going to put our guess and input byte variables inside. We're going to AND it with 0, 1, input, and input. We're going to use our helper function. We're going to track the number of correct. We're going to use the np arg sort to generate a list of indices from low to high. That's called our sorted list, and that's set equal to np.arg sort guess list. Setting it from low to high, it'll reverse the list to get high to low. And then we have a print method here in the for loop. So here we're storing each key score in guest list, where the index is the key guess and the value is the number of matching bits. For the loop, we call argsort to get the key guesses sorted from the best score to the worst score. And finally, we print the top candidates. In this example, we see that 0xEF sits clearly at the top with the highest match count. In a perfect 1000 out of 1000, and here that's what we get. Other keys are far behind, and that's precisely what real key recovery output looks like, a strong peak at the true key. In this case, we know that bit 0 was the leakage. What if we didn't know that? Imagine putting our needle down into the internal bus, but we aren't sure what bit we just touched. Luckily, we can easily test that. To do so, we'll need to adjust our leakage function to take in a bit number that is leaking. First, define a function which returns the value being 1 or 0. So far, we've assumed we know that the device leaks bit 0 of the SBox, but in real life, we might not know exactly which bit our measurement corresponds to. We might just have some point on the trace that behaves like a single bit. Here, for get bit, we're gonna create a is statement. So for each key and bit pair, we compute hypothetical leakage with get bit across all inputs and score against real leakage. The combination that yields the highest match tells us both the key byte and which bit is leaking. So finally, finish off this loop by adding our leakage function to it. Running the loop should print the results for each bit option. Hopefully you see that only the matching bit shows the full number of matches. If you want to try a different leaky bit, you'll need to go back up, secret key observation, make the leak happen from a different bit. But you can see the following code makes no assumptions about bit 0 being the leaky one. It will work with any bit leaking now. So here we're going to set hypothetical leakage equal to AES leakage. Yes. We're going to input our guess, input byte, and our bit guess. We're going to use bit guess as the bit number, guess as the key guess, and data from input data. Go ahead and print and see what pops up. So for bit 0, we get a 100% match for EF, which is to be expected. This all assumed you get some way to observe the value of the bit. In our next act, we'll see how power analysis gives us the ability to observe a given bit. Hope you guys enjoyed this today episode. That we were able to make it all the way through without any errors. Gonna wrap it up. I'll see you next time.